Hello fellow problem solvers, so today we're going to be doing a problem from the 2011 IMO Shortlist, problem number N2. I suggest you try this number theory problem out for a minimum of 10 minutes, ideally 45 minutes, but not more than 2 hours. If on the other hand you'd like to go along with us, I suggest you give it a go for the next 15 minutes. What are the first ideas that come up? And now without further ado, let's begin. So this is what the problem says. We have p of x is the product of x plus di for I 1 through 9, where these are fixed integers. And what we need to prove is that there exists some, after a while, there exists an integer and such that for any x greater than it, p of x has a prime divisor that's greater than 20. Now, for you, what is the first thing you do when you see this type of problem? For me, I know this is an N2, but even if it was at the IMO, I know that I'm not going to solve a problem to get a Fields medal. I know I'm solving an IMO type problem, which means what? I'm not going to do something on the distribution of prime numbers. That's way too complicated. There needs to be something simple, like a prime greater than 20. How do I get that? These are polynomials. Why 9? Why 20? And the first thing for me is, and here's the first idea, that how many primes are there less than 20? Let's see, there's 2, 3, 5, 7, 11, 13, 17, and 19. So 8 primes less than 20. We have 9 of these. There must be a connection. That's like the first thing for me. This is obviously almost like there's going to be a connection. What does this mean? This means for PF, for starting at some x, starting at some x, assuming the problem statement is false, that means you'll have a prime less than 20 dividing p plus, x plus di and x plus dj for some I and j that are different, i.e. p will divide their difference, di minus dj. And now here with this, I invite you to pause for, let's say, about next 10 minutes and try to push the problem further, get new ideas. And here's the next step. And the next sort of big idea is, wait a second. I'm not using anything about, I like doing things with primes, but I'm not using anything specific to primes. I can just use a regular divisor d divides this, and then it divides di minus dj. Assuming the contrary, we're assuming the contrary here, that there's, for big X, you will have instances where only these are the factors of px. And now, that means that there's some factor that's shared between two different x plus di, x plus dj. But really, this sort of thing is, if this isn't, these are different integers, right? So these are, this can't be true always. This limits what d can be. But if you think about it, be every one of these x plus di, once it gets very, very big, then its factors will, if they're all 2, 3 till 19, they're also all going to get very, very big. And now with that, if they're going to be, say, how much bigger do they have to be? How much bigger, actually, that's the question. How big do they have to be in relation to this? So, the question is, the idea is, if we have d that's big, that divides both of these, then it divides this. And now the question for you is, and this was the hint for the next 5-10 minutes, see how big of n do you have to find such that for all x greater than n, you'll have d dividing x plus di and d dividing x plus dj, such that both of these numbers, such that d is bigger than di minus dj for any I and j. So now pause for those 5-10 minutes and figure out what n has to be. Well, the way to really think about this in the easiest way is, for every one of these x plus di, let p to the alpha be the biggest prime among these, such that it divides x plus di. Let p be the one with the biggest prime. And then there exists 2 of them with p to the alpha, and p to the alpha plus something else plus dj divides this, right? But now, p to the alpha is if x plus di is equal 2 to the a1 times 3 to the a2 times all the way till 19 to the a8. Then alpha is the biggest one, so we know that like p to the alpha, like if we take every one of these to the alpha times 3 to the alpha times all the way till 9 to the alpha, like this is going to be greater than or equal to this. So now that's what p to the alpha tells us. And now we want p to the alpha to be bigger than this. Like, is this, we have this on one hand, and on the other hand, we have this is greater than 2 to the alpha, right? So, and I think this is what we need. We need this to be greater than 2 to the alpha, because what we really want is this p to the alpha to be greater than di minus dj. So, if we pick an x such that x plus di is greater than 2 to the power of alpha, where 2 to the power of alpha is greater than, like, what? Di minus dj, like the product of di minus dj, the absolute value product of di minus dj. So if we pick an alpha such that this is true, and we pick an n such that this is true for every di and every x, then we're done. And I mean, then we're done in the sense that then there exists like a prime p such that p to the alpha divides both x plus di and x plus dj. And then because this is greater than 2 to the alpha, we have that their difference is also divisible by p to the alpha divides di minus dj. But that means this is greater than or equal to p to the alpha, which is greater than or equal to 2 to the alpha, which is greater than di minus dj, which is a contradiction. So that's how we can get to a contradiction. And now here I invite you to pause for 5 minutes and write up a solution. Here's one of the solutions. So it's messy, but we say take m to be a fixed integer such that this is true. Assume the contrary. Take n to be this for every x greater than n. We take for each x plus di a prime such that this is true and alpha I is largest. Like we take a prime such that we have the largest alpha I. And by the pigeonhole, we have xi plus d and xi plus dj that have the same p. We estimate p to the alpha for both, and we have its p to the alpha is greater than strictly di minus dj, and then we get our contradiction. So this works, and this solves our problem. Now mind you, there are better estimates, I mean not better, but like lower bounds on the estimates, but this also solves the problem. And it's like this sort of, the idea is when you have sort of a product of, like, as you increase a number, its prime factors have to increase if the primes themselves aren't increasing. And I think that's just like a cool idea. I saw it in another problem, so I thought this would be a good problem to show you. And as always, thanks for problem solving.